Check, 1, 2. Alrighty, shall we get started? Yes, no, maybe? Maybe. Okay, let's get started. My name's David Fetter. I work for an outfit called Postgresql Experts. That concludes my marketing spiel for today. I would like to thank very much the FOSDEM organization for inviting me over here and for very kindly paying for my air ticket. That was really above and beyond the call. And I'm going to talk about some things which until now weren't really easy to do in SQL databases, or at least not in the free SQL databases that anybody had any experience with. Okay, so that's a lot of qualifiers. Is anybody using Firebird? Okay, well, so there is one free database that actually has this stuff, but I'm going to talk about it in Postgres. So one of the things that you find yourself needing to produce is these. Yes, thought somebody might notice that. You don't normally have to produce any of these in production, but it's nice to know that you can. And yeah, it's a little bright in here, but that's yeah. Okay. Is there a way to dim it a little bit, or no, not so much? I don't want to put anybody to sleep. Anyhow, so the things that make these that make it possible to do both of these things with your SQL engine are windowing functions and oops, oh, okay. Yeah, I don't see a light dimmer here. Yeah, really. Yeah, the seat ejector is the one I'm scared to touch. It's I don't know which seat it's going to eject and whether it's going to open the roof first or, you know. Yeah. Fluorescent illumination. No, you know, if I touch one of these things, I'm going to destroy it. I better not. Okay, so anyway, use your imagination a little bit. That there is a Mandelbrot set. So windowing functions are things that let you deal with lists, such as the kind of lists you would use when you're generating one of those TPS reports. Recursion is something you would use to deal with tree-like structures. Has anybody ever tried to deal with a tree-like structure in a database system and enjoyed it? Okay, well, we're going to bring the joy. Today we bring the joy to that process. So what windowing functions let you do, that's the list part. They let you see outside of the current row in your results set, which lets you make those TPS reports better. So for example, you could have a running sum, and a running sum is a kind of handy thing to have in a reporting system and in, you know, maybe a display on a point of sale system, let's say. So windowing functions operate on a window, and a window is in general a subset of a query. It may not, or of a result set. It may not be a proper subset, so it may contain the entire result set, but it's some chunk of a result set which you've carved off. It returns a value for each row in the window, and then it calculates the value from the rows inside the window. Windowing functions let you use the new windowing functions, some of which I'll show you as we go along. And existing aggregate functions like sum and count and yes? Oh, okay. By the way, interrupt any time, and if I'm if I'm not paying attention, just like scream or throw things. That usually gets my. Okay. You can also make your own user-defined windowing functions, although those you need to write in C right now, and we don't really make any guarantees about the stability of the API. So you're kind of off the map there if you go to write your own windowing functions, but you can do it. And of course, you can use any user-defined aggregate functions, which, has anybody made a user-defined aggregate function for both? Oh, great. That's more than usually say so. So what does yours do? Doesn't remember. So your aggregate function would ball up a set into, or a bag into a set. It would uniqueify a list. Oh, that's neat. So anyway, you could use it in the windowing context right away just because of how windowing functions work. So basically, there we go. Here's how aggregates work. They sort of they crunch together things from a larger set down to a smaller one. With windowing functions, you get sort of more of this effect. You get a kind of cross-mapping thing where you get an effect more like this. So one of the first things you can do, or the easiest things to demonstrate with windowing functions and why they're helpful, is numbering rows in output. Now I know Oracle has this thing called row number, and that's kind of handy. I don't think it's it's done in the standard way, but you know, Oracle has got its own standard. But has anybody tried to do this inside Postgres before? Get row numbers? Yeah, not fun, is it? No. So we're going to add some fun, but here's how we used to do row numbers. So you have the classical employee table, and you join it to the, no, this is emp salary. So basically what you want to do is take the employee number, department name, and salary, count star as row number from emp salary E1 join emp salary E2. So you're going to join it to itself, and then it's sort of a cross join. So so you get sort of the upper part of the triangle of the cross join, and then you group by this and that and the other thing. And so is this query going to run really fast? Anybody? Fast? Yeah, it's quadratic. It's gonna get a nested loop join, right? It's gonna be super unfun for performance, and we got lucky, right? We noticed it's obviously wrong. If you're doing hacks like this, in order to get windowing kind of behavior, it may not be as obviously wrong as this is. And when it is unobviously wrong, the people who remind you that it was wrong could be forensic accountants, for example. And by the time a forensic accountant is reminding you of anything, you can be in real trouble. So you don't want to go there. This is why the SQL standard has these windowing functions which allow you to do this. instead of cross joining the table to itself, you just select from the table, and then you have this construct here where you have a windowing function. In this case, it's called row number, and then it says, and then over, and here's where you can define a window. You can also define it elsewhere. We'll go over that later. You say over, order by salary, descending, nulls last. Okay, so you have an ordering in there, and that's how the row numbers are going to come out. So if two employees have the same salary, what's going to happen here? Anybody? First. Okay, yeah, the answer was first one gets first, but since we haven't defined an ordering here, it's unspecified and you will not be able to reproduce the result. Or you won't be able to guarantee that you can reproduce the result. So when you're defining your windows, you need to think carefully about the ordering that's in there and is it sufficient to make a deterministic output. Or, you know, you could decide that you don't care about determinism at some level of the output, but you have to at least sort of think that through. So that's what our query looks like, and of course our row numbers have come out right. In addition to row number, which unconditionally increments as rows come out, you can also have rank, which looks for ties, and then orders by those. So if your numbers or let's say you have ACCCF, so what you get there is a rank like 1, 4, 4, 4, 5. That's what rank would look like, corresponding to ACCCF. And dense rank, you'd see 1, 2, 2, 2, 3. In other words, dense rank sort of collapses the ranks that you'd get. Questions so far? Comments? Anybody still awake? Okay. Yes?
Can you get 1, 2, 2, 2, 5? 1, 4, 4, 4, 5.
No, you'd get 1, 2, 2, 2, 3 with a dense rank.
Not dense rank.
I think.
That's actually what it does.
Oh, okay, my mistake. Thank you. It actually piles the ranks towards the top instead of the bottom. Thanks for noticing that. So here are the built-in windowing functions that got added in 8.4. Row number, rank, dense rank. Well, you can read all those here if you really want to. I'll demonstrate some of these and how they work. So we've seen row number, just bumps it unconditionally over the window. This can be handy for, you know, numbering results. Rank we've seen. So there's a gap. So I guess maybe I was mistaken about being mistaken here, because because we have two here. Yeah, I guess we do. So there can be gaps in between them, and I guess it piles it towards the top instead of the bottom. Dense rank just closes all those gaps in your ranking. Percent rank scales normalizes it, not in the sense of database normalization, but like in the sense of a vector. So it squeezes it all into the interval from 0 to 1. That's percent rank, which is the regular rank normalized to that interval. You You can also look at cumulative distribution, which is, any statistics geeks in here? Okay, well, good. Then you know more about this than I do. I hope it's useful. Entile, so, quintiles or quartiles or three aisles, I forget. That sort of divides things into buckets and says which bucket it's in. Let's see, lag. This one's kind of handy. It basically returns the value of the row above, or you can parameterize it to say lag by how much or how many rows. So the first one doesn't really have a row above, so its lag is null. Similarly, lead takes the row below, and of course the last one in the window doesn't really have a row below, so we have to call that null too. First value takes the, yes? First value takes the first one in the frame, or in the frame. Similarly, last value, you have to add some extra frippery here, which will be on the slides, which I will publish as soon as we're done here. But basically, it takes the last value in the frame. Nth value, I guess this was the SQL Standards Committee's version of humor. Because I have not seen anywhere yet where you'd actually need the nth value. Has anybody else seen one? No? No. Okay, well, for completeness, I present it here, but it just, yeah. Okay, so windowing can affect aggregates if you want it to. One way it can, so here's where it's not affecting aggregates. We're selecting value in the sum over the empty window, which basically means we're not specifying anything about order or partitions or anything like that. We're just saying sum, and so it just acts like the sum as it usually did, except that instead of bunching it all together, it's repeating the sum at each row. Is that fairly okay? But the sort of more interesting thing that you can do with this windowing function over aggregates is that you can change aggregate behavior. So what we've said is value sum of value over order by value descending from table. So what's happening at these first two rows is that since you have not distinguished one from the other, they can't really be separated one from the other. So in the first two rows, your sum is actually the sum of the first two rows because they tie. Is that fairly okay? So again, it emphasizes that you have to at least think about what the ordering is going to do to your result set, and how much you specify. So if I'd said order by value and maybe something else which distinguished the rows one from the other, then you would see 5, 10, etc. Okay, so yes?
The other ones which would only work on a partition, why is that? The lag and the lead and
The question was the other ones which only work on a partition, lag and lead. Why is that? Well, you can partition your result set into different slices, and when you say you don't actually need to have a partition by clause in your windowing function, but if you do have it, lag and lead will only refer to the stuff inside the partition and not the whole window. Right, so if you've said partition by ID or partition by last name, it's going to do the lag and lead only in the context of the partition that you have sliced off. Does that answer your question?
So if there's no partition at all, it shows the whole thing. Shows the whole result.
Right, so if there's no partition by specified, then the frame is the window and you're done. Thanks. Okay, so that's enough about the TPS reports. I don't want to put you all to sleep too much. Well, you know, it was a large night for some of you last night, I imagine. So I'd like to talk about something else that's really new and different in SQL, and that's recursion. Everybody read that? Is that legible back there? Okay, so we have a Google result set, and I'm looking for recursion, and it says, "Did you mean recursion?" Yeah. Okay. So recursion is fun, and you know it can actually come up in real contexts. I'm going to show you how we generated that little diagram earlier. So we introduced a few little chunks of syntax, and here's the first one. So we say with recursive x of I. Okay, so what we're doing here is we're saying here we are going to make ourselves one or more temporary views or subroutines, whichever way you want to look at it, which are good for the context of this query and then will vanish. Right, so we say with, and then recursive is an optional keyword, and that talks about whether the views or subroutines can refer to themselves. And then we define the name of the view and the names of its columns optionally. So you don't have to name the columns, you do have to name the view. So you've named the view, and then we're going to define what happens inside the view. So the first thing we do is get us a 0 value up here. Sorry, has anybody got a pointer? So that's the first step in the recursion, is that when you recurse, you have an initial condition, and then you have some sort of a recurrence relation, and then if you're smart, you'll also have a termination condition, just in case. Yeah, so you say in the recursive view, you say initial condition union or union all. What would be the difference between union and union all generally? Anybody? Sorry? Yeah. Yeah, the answer was unique strips out duplicates, and that's what's happening. So union all would just pile everything together, ignoring duplicates. Union would strip them out and will cause a performance, change, because it has to then do that stripping. So union all is usually faster, and if you know, as in this case we do, that the results are already unique and that's how we wanted them anyway, we can just say union all. So you start with this temporary view, which just has one row in it, and that row is a 0. And then we say select I plus 1 from X, that's our recurrence relation, where I less than 101. And that means if we keep going, except that we have to check that I is less than 101. What happens if I leave off this where clause? Yes, it continues counting, and well, it continues counting until you overflow integer, I think. Yeah, so be careful when you're doing this. So what I've done here is I've generated some number of points in the x-axis, I suppose. How many of them? It's 0 to 101 because it can actually get to 101 before it stops, right? So it's 102 points. It's really easy to get off by 1, isn't it? I mean, it's not just C where you can do that. It's all kinds of places. Okay, so we have this set of points. Now we're going to make some more points, which are looking more Cartesian as we go along. So we select ix, iy, x float, y float from, let's see, do a little affine transform here on both of the result sets and cross-join them with themselves. And has anybody here done a cross-join on purpose before? Good for you! How about by accident? Yeah, it's really easy to do a cross-join by accident. You just say from table 1, comma, table 2, and you forget to put in a where clause, and then you get a Cartesian product. Okay, so we've picked from this sort of affine transform of 10,400 and anyway, it's around 10,000 points. And then we're going to do this recurrence relation. So we have our little union all here that signals that we're in a recursion. And then we're going to sort of, do this little quadratic mapping thing and bound it. And 27, wonder what that could be. Well, we'll find out, I guess. So that's our next subroutine. Is we've taken the set of 100 points and then we've somehow transformed it into this block of 101 by 101, and then we've iterated over the block for some number of iterations. So once we've done that, we have this giant result set that we need to slim down because we don't want to be in 127 dimensions. We want to be in 2. And the way we do that is we project this into the Cartesian plane by just choosing ix, iy, and the max I. So we just sort of collapse those results into the biggest one we found. From Z, group by ix, iy, order by ix, iy. Okay, so we've now got a set of 101 by 101 points, and we want to be able to display them. Well, in the grand tradition of ASCII-matic, we're going to display them by indexing into a string, right? So we're going to, things that have 1 are going to map to a space, and 2 map to a dot, all the way out to 27, which maps out to a space, or 26, I think. Okay, and we say greatest of I comma 1, which is to say that if we happen to have, an I that was 0 or negative, we just call that I a 1, just in case, because we already choked off I to be less than 27. Right? We just want to make sure it fits in the array bounds, because otherwise we could have this, we could have some sort of a Stack Overflow kind of attack, and who knows what could happen. Right? So we mapped it, we've grouped it into an aggregation and then collapsed the aggregates into a string, and voila. Okay. So that was actually a fairly easy problem as math goes. How about let's try a somewhat harder problem? Like maybe, yes?
When you're computing the building block iteration,
Yes.
you're loading a bunch of rows, and then you're getting the maximum of the iteration for each point. So you can know what character to display.
Yes.
My question is, do you actually build all the rows, one row for each iteration somewhere before collapsing them?
So
Or
the
planner optimize this
right.
somehow?
So the question was, does the row set actually materialize into memory? And I believe the answer is yes. Well, you know, nothing comes for free, and it's unfortunate, but there it is. Okay, so back to our slightly harder problem. We're going to try something that's NP hard, right? So we have a traveling salesman problem. This here is a reminder to make sure that before you start embarking on an NP hard problem that you actually have to solve that problem. Can everybody read this? But assuming that you do have to solve the problem, you have to set up data structures and you have to start, you know, doing your computation on those data structures. So that's what we'll do. I'll have a very simplified schema. It'll have a table, it's called pairs. We got a from city, a to city, a distance in between. We're going to say that from city and to city defines uniqueness on this table. And then we're going to check from city less than to city. Why do we do that? Sorry?
From the city to itself.
Well, one answer was from the city to itself, but that's, yeah, that's part of it.
You don't want to do it in the opposite direction.
You just want one, several people said you just want to go either here to there or there to here, but you don't want to have what could be different distances. So we're assuming that the distance between, say, Bari and Bologna is the same as the distance between Bologna and Bari. And so we just limit it to only representing one of those. Okay, so we have our table. Let's insert a little data in there. Bunch of, I forget where I got this, but it was important. Sorry? Yeah, well, maybe. Okay, so now that we have our data structure and then it's populated, we need to do some computation on it. And by the way, the computation we're doing is sort of a cheating version of brute force. And I'm cheating because I want to make sure that, well, that the program terminates in a reasonable time. And I'll show you how I cheated in a little bit. Okay, so having made sure that we can't actually have the paths in both directions stored in our table, we now proceed to double the size of the table so that we get all the paths in all directions. Is that, yeah, okay. So that's what we're going to do here, is we say from city to city and distance. We said with recursive, and there's a union all down there, but it's not actually a recursion. We just said with recursive means that we can use recursion somewhere in the common table expressions or temporary views or subroutines that we are about to create. So we select the distances in one direction, from city to city distance, and then we hello, select them in exactly the opposite direction, to city from city distance. So we just doubled the size of the table. We want all of those, edges for our graph, right? The one way and the other way. Okay, so we've got that data set, and then we try a little initializing a path. So we're starting out from Rome, and that's going to be our from city. We say to city, and that's all the possible places you can get directly to from Rome. The distance in between, and then we're going to just put Rome in its own Postgres array, which I think is fairly standard. I'm not sure, I haven't checked with the standard on how arrays are handled, but it's a very handy thing to have around. And we pick that from the both ways result set, which we've just created. By the way, anybody want to guess why we had to pick this as a starting city? Thank you. Little geek humor. Sorry about that. Okay, so now that we have the paths, paths that go from Rome to one other city, we need to keep going until we get back. So we've got those going outward, and then we want to choose more. So we starting from the endpoints of our previous our previous hello. I'll just draw it right here. I hope everybody can read it. So we have Rome, and we just did this to each of the cities which are directly accessible by one hop from Rome. So then we're going to start from each of these and go on to other cities and so forth and so on. Is everybody, is that fairly clear on that? More explanation, less? Faster, slower? Okay. We join back to that previous result set that we just created. And we join on head to tail sort of for the edges, right? The tail of the next edge is the head of the last edge. Then we make sure that the from city is not in the path except for the first element, right? So we want well, okay, so why would we do that? Sorry? We do want to get back, but only once. So we don't want to have extra loops in there. Our salesman is supposed to travel in as short a time as possible, and looping infinitely is probably not it. So we only want the one cycle, and that's why we have left off the first element in the array, which is where we're trying to get back to. I also remember the part where I said I cheated about this. Can everybody read this okay? It says array upper of p dot path comma 1. That means the first dimension in the array, its upper bound is 6. So basically, we're saying we got to get back there in 6 hops, and if we don't get back there in 6 hops, it's probably not our shortest one anyway. Why would we say only some specified number of hops? Anybody? Nope. The answer was total number of cities. Actually, what it is we're trying to prevent the sun from burning out while this query runs. And
But if that's less than the total number of cities, you must find a solution.
well, if it's less than the total number of cities, we would hope to find a solution in some smaller thing than start at Rome, go to every other city in Italy, and come back to Rome. Which is what you do if that would be the longest path, basically. You actually want the shortest path that hits the cities described, which I had to describe below because of some limitations in our implementation. So we said, start at Rome, hit these 3 cities, and come back. That's what the traveling salesman problem is all about.
So you're limiting to 3 cities.
So I'm limiting. I'm saying that I have to hit 3 cities, and I hope that in the process of hitting those 3 cities, I only hit at most 6. Okay, so this is just to prevent the sun from burning out and me from getting bored and you from getting bored while we're doing this exhaustive search. So it's not actually O of n factorial, which is pretty good because there was like 60 cities in there. And 60 factorial is kind of big and long and boring. Okay, so now that we've got these paths, we'd like to find the final one where, so we've got all the paths that have Rome as a starting point and are less than 6 long, and don't have Rome in them. So we have to finish this off and say, well, of those, some of the paths will be 1 hop away from Rome again, and those are the ones we want. So we're picking all the paths with Milan, Florence, and Naples in the path. So those are the cities we wanted to visit. I still haven't gotten to Milan and Naples. I hope to someday. Anyway, so we want to order by distance because the idea of the traveling salesman problem is that you want the minimal distance. So we're saying distance ascending, and then order by path also. Why would we do that? One answer was get the shortest pathway. It's actually, we already took care of that by distance. Any other guesses why we would order by path along with distance? The answer was eliminate duplicates, and that's right, because if you go one way through a path and then go back the other way through the same path, they will have the same distance according to our model. So that's one of them. And another one is if it happens that two completely distinct paths, or at least 2 partially distinct paths, have the same distance, we just want the same answer coming out each time we run the query. Because if we have a tie from 2 different paths, we just want to trim it down to 1. Okay, so that's our traveling salesman problem solved in 12 seconds, which isn't too bad for brute force. Let's see. Well, I was going to go through some things about posting on a forum, but apparently I have taken too much time. So right now, I would like to, I'll post this later. And I would like to, oh yes, by the way, SQL is Turing complete, so just be really careful about what you let people execute SQL on. And I would like to open up the floor for brief questions, comments, and of course the straitjacket I've just earned. Questions, comments? Alrighty. Thank you so much.